Hello, this is Christos, and this is a presentation of my work with Marius Miron called Music Arrangement using Hierarchical Segmentation. So what is music arrangement? Well, let's say we have a music recording that is 2 minutes and 48 seconds long, and we're creating a video that is only 1 minute long. How can we make the recording match the duration of the video? Well, this is quite a common scenario in audiovisual content creation, in cases such as advertising, vlogs, short-form video, podcasts, and even film. So how do we go about this? We could stretch the audio, but that means we're almost tripling the tempo of the song, which won't necessarily sound natural. We could instead trim the song, but then we would have an abrupt start and ending. So what is very commonly done is rearranging, taking parts of it, shuffling them around, and then creating a new song out of them. But this is a time-consuming process that needs to be done by a music engineer. So to be precise, a rearrangement is a standalone piece of music. It makes sense on its own. It has a different duration to the original. It only contains non-edited parts of the original. It has the same start and end as the original. And finally, it has not introduced unnatural discontinuities. So how has rearrangement been approached in previous academic work? Well, it's been primarily treated as a cut point identification problem. So what pair of points in the audio, if stitched together, would produce a natural, imperceivable transition? Focusing solely, however, on finding smooth transitions can lead to unwanted repetitions and does not allow us to control the musical development of the piece. So in what axis can we improve rearrangement? Well, we propose the axis of balance, how repetitive or variable a rearrangement is, good development, how natural the continuation of musical ideas sounds to the listener, and of course also how smooth the transitions are. Our approach to this problem is composed of 4 steps. We first analyze the hierarchical music structure from the audio recording. We use this structure to find suitable transition points between segments of different structural function. We then find suitable transition points within structural segments. And finally, we construct a path using these transition points. To compute the hierarchical structure, we use the spectral clustering approach proposed by McPhee and Ellis, with the subsequent feature improvements proposed by Salomon et al. The aim of this method is to construct a structure encoding that reflects the global repetition patterns, as well as the evolution of timbral features. To do this, we first compute the constant Q transform from the audio, as well as features from a deep music tagging model. With these two, we aim to capture melodic, harmonic, rhythmic, and other elements of the piece. We also compute a representation from a few-shot sound event detection model in order to capture timbral aspects. From the CQT, we compute a weighted, undirected recurrence graph. A notable difference between this approach and a self-similarity matrix is that only vertices of the graph that are similar enough will be connected. We do the same thing for the deep features. For the few-shot learning embeddings, however, we construct a sequence matrix, encoding the evolution of subsequent frame similarity. We compute a weighted combination of these graphs, which we filter to enhance the diagonals. Processing this graph for clarity, you can see connections between frames. Diagonals indicate that sequences of frames match with other sequences of frames, indicating a repetition pattern. From the combined recurrence graph R, we compute the symmetric normalized Laplacian. This helps us go from a graph to a matrix that we can more easily analyze. We decompose this matrix and take sets of the k first eigenvectors of the matrix. So for example, the set for k equals 3 contains the first, second, and third eigenvector as ordered by their eigenvalues. To get a better sense of these sets, we can plot their self-similarity. We can see that these act like low-rank approximations of the Laplacian. So for example, for k equals 2, we can see fairly large structural components. The more granular we get with a higher k, the more granular the approximation. For each set, we then apply spectral clustering, where for set k, we use k number of clusters. This results in a segmentation of the recording at multiple levels. Segments of the same color belong to the same cluster, and therefore have similar structural function. Now that we've grouped musical ideas in this way, we can think of rearrangement as the reshuffling of these structural segments. Since segments of the same type will have similar musical information, we add the restriction that a segment can transition to a segment of the same type, helping us avoid repetitions. However, practically, segment boundaries might not be ideal points for transitions. This can be for various reasons, like for example, effects like reverb leaking into the succeeding segment. We therefore propose an algorithm for finding more suitable transition points around the segment boundaries. Given a segment boundary, we take an area around it with a radius of 4 beats and search that area for suitable transition points. To do this, we look at the same recurrence graph that we constructed. As mentioned, while single points indicate similarity between frames, diagonals indicate similarity of sequences. The longer the diagonal, the longer the sequence that is similar across 2 points of the recording. This makes diagonals more reliable than single points as transition points. We therefore search in an area of radius 4 from the anchor beat and the target beat to find the longest diagonal, indicating the most suitable transition point. The edges in the recurrence graph are weighted, so we can take advantage of them to assess how similar the entry and exit point will be. In the case where we find no diagonal that is at least 3 points long, we take the segment boundary as the transition point and set the cost of this transition to 1, since it's non-optimal. If we do find a better neighbor point, then we weigh the cost by the similarity of the points. And if the entry point is further ahead in the recording than the exit point, we penalize the transition with a factor of 4, so that we discourage backwards transitions, but still allow them to happen when we create rearrangements that are longer than the original song. While we found transitions between non-similar segments, the truth is that long segments might contain repetitions. For this reason, we are interested in identifying transition points so that skipping these repetitions is possible. We use the same algorithm as before, only this time we only consider neighborhoods inside the segment boundaries, and calculate the transition costs in a similar way. Finally, with these points, we construct a path. If we let A be the desired rearranged path, then we need to minimize the transition cost between 2 consecutive beats of A. This will be subject to the first beat of A being the first beat of the song, and the last beat of A being the last beat of the song, meaning the song retains its start and end. A beat can only be succeeded by the next beat or by another beat if the transition between these two exists. And finally, the duration of A needs to be within a tolerance of the target duration. As proposed in the previous approach by Stoller et al., we used Dijkstra's shortest path algorithm to find the optimal path A. So let's have a look at the evaluation. Unfortunately, to our knowledge, there currently aren't any open source, publicly available music rearranger systems. That's why we opted to compare our system with Adobe Remix, a tool implemented in Adobe software such as Audition and Premiere Pro that does music arrangement on the timeline. We also asked a music engineer to produce some arrangements manually for us. We designed a survey with 5 songs from different styles and traditions, each rearranged at a different target duration. We had to keep these short, as for 5 songs and 3 rearrangement systems, the total survey time was already 20 minutes. We used a 5-point Likert multiscale with 4 axes, and a total of 17 participants took part in the study. The results for each axis are shown. We see that the manual rearrangement did not receive perfect scores, probably indicating that there is some subjectivity to what makes a good rearrangement. Our system performs close to the manual rearrangement in this study, outperforming Adobe Remix with this limited sample size. We also see that Remix fails to make a good rearrangement for song 1. This was because the transition it selected was only similar for a single beat rather than a longer sequence of beats. Overall, further experiments are needed to disentangle between preference, recording quality, and arrangement quality. The study was severely limited by the listening time required, meaning we couldn't test any rearrangements that were longer than the original piece. We believe that in order to test different parameters and cover a wide range of traditions and styles, a quantitative evaluation needs to be devised, but it's not trivial how to design it. With that said, we are releasing the full code for the Music Rearranger, and we really encourage you to try it out, use it with your music, modify parts of it, and find what parameters work best. In any case, thank you for listening.